Hi, my name is Fazdlie Aqmal by YUSOFF. I am Bachelor of Operational Research with Data Science from Universiti Pertahanan Nasional Malaysia.
I am YUSOFF, a senior lecturer at Department of Defence Science, Faculty of Defence Science and Technology, UPNM.
Hi, I'm Dr. Norain Azimi with Partner C, Senior Lecturer at Department of Mathematics, Center for Defence Foundation Studies, Universiti Pertahanan Nasional Malaysia.
Hai, Assalamualaikum. Saya Nurdiana binti Kamarudin, merupakan salah seorang ahli penyelidik di dalam research team ini.
Assalamualaikum and hi everyone. Today we are from Universiti Pertahanan Nasional Malaysia, UPNM, and we will be showing you our project presentation, which is estimating network fundamental diagram using principal component analysis based strategy, a case study of urban transport networks. Metropolitan cities consistently struggle with traffic congestion. Several factors contribute to it, including dense population, economic growth, and increase in automotive use, inadequate roads capacity, inadequate city planning and management, incidents, and weather factors. Traffic jams cause vehicle delays and related costs, which have a considerable negative impact on social, economic, environmental, health, and well-being. Hence, preventive action on alleviating traffic congestions are essential to take. One way of effectively monitoring of measuring traffic congestion level in metropolitan road network is by using network fundamental diagram (NFD). It is basically an asymmetric inverse use diagram which depicts objective network performance by connecting infrastructure regional mean, velocity, vehicle movement, and flows. The NFD is well-known diagram used to measure urban network aggregate traffic conditions. The NFD enables transport developer in management by providing network status data and showing whether the system is functioning in the NFD's green, yellow, red, or dark red zones. The red zone is a dangerous traffic situation. Lineups arise when a network of cities get crowded, causing the flows to decrease, travel time to increase, and infrastructure to be underutilized. As a result of this data, the traffic controller will seek to keep the network from being oversupplied while still serving traffic at the required level. To achieve maximum flow, the network should be operated at or below critical occupancy accumulation. This goal is achievable with good traffic management. The concept of a basic diagram, as seen in structure of a flow density curve, seen in this figure, has recently been demonstrated to be applicable to dimension urban road network under certain conditions. When network capacity is reached, the traffic flow grows up to the yellow region in the two-dimensional basic graphic. When the essential density limit yellow zone of the system is reached, it begins to deteriorate and finally enter to oversaturated area red zone. The purpose of transportation analysis is to maintain to the traffic state in yellow area by utilizing different traffic control methods such as traffic signal improvement gating, route advice, and so on, as well as to prevent overflow and congestion production shown by dark red, in which the flow is close to zero in this figure. So in this research, gate control is employed as an effective transportation methodology to maintain the traffic condition in the yellow zone. Research objective. Generally, the purpose of this research is to find the best links to use as material resources, detector, or sensors to collect traffic data in order to calculate an accurate NFD. The purpose of this work is to pick sensors using a symmetric technique based on principal component analysis (PCA) to enable the creation of sparse measurement NFDs that need fewer sensors, appropriate measures, and are in theory less expensive. There are three objectives implemented to reach the goal, which are as follows. First, to develop a framework for sensor selection problem in transport networks using PCA. Second, To examine the performance of suggested method in producing reduced NFD with a minimal number of sensors. And third, to examine the accuracy of the suggested approach. Data collection. The test site of an urban network of China's Central Business District (CBD) in Greece is used. The network consists of 70 roads or links, 68 sensors, and 24 signalized junctions. The links in the network are of various lengths, varying from 50 meter to 500 meter. Real data consists of flow and occupancy from 58 census links of 1 week are ready for experiments. The measurements were in 1.5 million samples of flow and occupancy. The occupancy of lane were aggregated to 6 min all lane and averaging, and the flow were aggregated to 6 min all lane and summing. These data are then used in an offline mode. The procedure for research methodology illustrates the hierarchy level in this study by stating the aim, objective, data collection, and methodology. So, for the first level, the study aims to find the best link to use as monitoring resources. For the second level, the objectives are divided into three, which are to develop a framework for sensor selection problems in transport networks using PCA, to examine the performance of the suggested method in producing reduced NFD with a minimal number of sensors, and to examine the accuracy of the suggested approach. For the third level, the data collection will be divided into two, which are occupancy and flow. As for the last level, the methodology is divided into three phases. For the phase one is the principal component analysis, whereby it's divided into two, which are B-plot and loading value. Phase 2 is the estimation of reduced NFD, and lastly, phase 3 is accuracy measurement, whereby divided into two, which are RMSE and characteristic. So these results for case 1, which is reduced NFD approximation. In this figure depicts the sub-measurement NFDs, circle markers in color, obtained to all experiments in case 1 when contrasted with the empirical full measurement or reference or ground truth NFD, filled circle markers in black. As can be seen, the reduced NFD is well approximated, although by using 40 links. All experiments were observed to retain the shape and characteristic of the operational full measurement diagram. In this figure also depicts the best fit approximation of individual cases as well as their comparison with the reference NFD. Case 1 until 4 provide a good estimate based on eye observation. Meanwhile, the associated B-plot were shown in this figure. Close examination revealed that the NFD approximation was improved when the scores red dot in the B-plot were near the specific variable marked by label. For all experiments in case 1, this hypothesis was successful and demonstrated. With the provided PCA framework, this finding offers a promising outcome. To further assess the efficacy of the PCA framework, several strategies of sensor selection were implemented, namely Case 2. According to Safari 2020, variable sensors in PCA with the highest loading values normally produce a good level of approximation. Surprisingly, for our study, the findings were contradicted. In this figure depicted poor examination when choosing high loading value in first principal component. This comparative study analyzed estimation of NFDs using increasing number of links, namely case 3. Description of experiment involved are as following in this table. It is observed that when number of links increased, the approximation of NFD was improved. As we can see in table estimation errors, the blue box in case 1 is range of critical occupancy and flow capacity for Monday occupancy data, which is 25 and 500 SST, where is acceptable in range where compared to the blue box in full measurement NFD Monday in a range of critical occupancy, which is 17 until 27, and flow capacity, which is 470 until 570. For the accuracy, we can see that in the green box shows a smaller value of RMSU QO compared to the red box shows a highest value of RMSU QO. It can be observed the case 1 is more efficient than case 2. Conclusion: experiments were carried out using real loop detector data on urban network CBD of China. Principal component analysis was implemented and then links were selected based on loading value and from bplot. Network fundamental diagram then was estimated based on selected reduced links. According to the research conducted, PCA with the help of bplot provided an aid in identifying best links and gave good approximation case 1. Meanwhile, method strategy based on high loading value, radius or blind strategy gave poor approximation case 2. This study is important in identifying critical link in urban network where it can help monitoring managing traffic congestion. Future works include to use special type of PCA which can cater spatial data as in Joliffe 1972, Joliffe 1973 and Joliffe 2022.